let's try to define electric potential difference. So here is the definition in terms of an equation, but of course we want to try to break this whole thing down. I am assuming that you're familiar with charge, you're familiar with an electric field. I put up a link up above there. You are familiar with displacements, so those concepts are very familiar to you. You're also familiar with the equations that you see here on the screen. For example, for the force, which is caused by an electric field, here is the electric field, the magnitude equation. Here's your constant, okay, that we will use. Now, electric potential energy is defined in the following way, and I'm using a definition from a textbook. So it states that it is the energy which can do work on a positively charged particle. Now, it's not just on a positively charged particle, so we're going to be calculating, and you should be able to calculate what that electric potential difference is. Doesn't matter if it's positive or negative, but in terms of the definition, that's what we will reference to. So it is reference, okay, with respect to a positively charged particle. So obviously the signs will change, okay, if you're going to be computing this thing out. Let us first start with gravitational potential energy, and I'll show you that the explanation is identical, and it will hopefully make you understand the electric potential difference in a much easier way. So most students will study gravitational potential energy in grade 11. And when you study that in your foundational physics class, then you are going to run into this particular equation for it. That the gravitational potential energy that you have is nothing else but simply the mass of the object. And this is the mass that you see there. That's the red circle that I drew, multiplied by gravity, and then whatever height that you might lift this object to. And now if you hold it there, it has potential to do work. So if you release it, it has a potential to do work for you. Now, this concept came through the realization that if you notice that mass times gravity is just weight, or it is the force of gravity that you would have to overcome, and then this h would have been just the height or simply the actual displacement that you would have to move. Now, this concept that you have in here, the higher that you move the object, now of course this is around the Earth's surface, the more potential energy that it will have. So, as you keep moving it higher and higher, and it is relative to some surface. It doesn't have to be the Earth as I've drawn it. It could be with respect to a table or something else. But the idea is that, the higher you lift this object, the more potential energy that you give it. Okay, and then the lower it is, well, then it will have less potential energy. So now the question might arise, well, what if we're not interested in how much potential energy it has, but what is the change in potential energy? Okay, so what's the change in potential energy? So if I would take this and all of a sudden, so it has a certain amount of potential energy up above there, which is governed by that equation. If I bring this back down to its original state where it was, right there, and let's say it's touching the actual surface, then it lost all of its potential energy, correct? So the potential difference would have been negative. Now, why is it negative? Well, because at some point up above here, well, this is the potential energy that it had. So that would have been the potential energy at that distance. Now, all the way over here, its potential energy, assuming that it's touching the surface, would have been approximately 0 that it would have. Or if it's just above there, we know that the amount of potential energy up above here is more than it is down here. So if you're going to bring this back down here, it's going to lose potential energy. And therefore, the difference, okay, that you would have, so this is the difference that you have, so delta, in the change of the gravitational potential energy would have been negative, right? So this would have been less than 0. It has been losing potential energy. Now, if you let it go, it probably would have been picking up kinetic energy. So that isn't anything new for you. Now, if we went in reverse and we, for instance, said, okay, well, what if we took this mass and we started to lift it upwards, okay, all the way, maybe all the way up on top here. So at some point, well, what is going to happen to the potential difference of energy? Well, in this case, it would have been gaining potential energy the higher that you lift it. So therefore, if you're going to lift it up here, so all the way through, the actual difference in potential energy would have been greater than 0. So that's the difference in between. And that is just governed by that equation. Now, let's take a step backwards again and think about, okay, where did that equation come from? Well, the equation actually came from recalling that we had to calculate a certain amount of work. Now, what exactly was work, okay, as we went through in terms of its definition? So there's various ways, just depending on how much background students have. I'll try, okay, to talk about the definition of work, which is related to the amount of force that you would have to exert. And this would be multiplied by the actual displacement that you have. Now, these two were vectors, so we typically would take the magnitude of these two. And then, funny enough, we had to multiply this by the angle, okay, or the cos of the angle in order to find out work. Now, if the angle in between them is 0, then cos of 0 is just 1. Now, I can point out you to that work definition, okay, so from way back, okay, if you wanted to know that. So for us, so within here, so if we take this and the angle is actually 0, then in this case, this just simply equals to 1, and then all we really have, I'm going to drop the magnitudes there, so it's just force times the displacement. Well, the amount of force that you would have to use is nothing else but overcoming the weight of the object, and of course the weight of the object is mass times the gravity, and then the displacement, it was actually the height. And hence, we have found our gravitational potential energy, so this would have been the amount of work that needed to be done in order to lift that object up. Now, if you wanted to know the difference, okay, so the losses and gains of work, that is the potential difference that you have. And therefore, you might run into this being either negative or it might be positive, just depending on which direction, okay, that this mass is going. So if it's going from the bottom to the top, it's gaining, okay, energy, and you would have been actually losing it, okay? So that would have been gaining potential energy, and if it comes back down, then it is losing potential energy as it comes further and further down. So now what we can do is, I'm going to actually steal this entire thing, and I'm going to do exactly the same thing, because you might be wondering, what in the world, okay, is this guy talking about, and why and how is he relating this towards the items for electric potential energy? So in electric potential energy, well, we are not under gravity, so as we were in here, so these arrows kind of represented the gravitational field that you have, so the gravity which would be pulling these objects down. Well, instead of gravitational potential energy, well, what we would have is we would have an electric field. Now, what is an electric field caused by? Well, it's caused by some distribution of charges. So those particular charges, I'm going to kind of take this and bring it back up here. And let's imagine that we have kind of two plates in here. And these two particular plates, they would have a charge on them. So we have, let's say, a positive charge within here. So this is positively charged. So these would be like positive charges all the way through. You can even imagine it's just one charge. And then you have negative charges all the way through here. So this is, when we draw this out, by convention, the electric field is pointing in the direction from positive to negative. And the reason for that is because if we put a positive charge there, so somewhere, well, what will happen is it's going to get attracted to the negative charge and it's going to get repelled from the positive charge. So therefore, if this instead of a mass is an actual charge, and this charge is a positive charge, so instead of just being a mass right here, let's put a little plus, this is a positive charge within here, then what is going to happen in here? Well, what we know is that if we left this charge, now of course, let's assume that, so this charge is over here, and let's say this charge is, nowhere, okay, so I'm going to just remove it for the moment. So if you left this alone and you put this in an electric field, then that particular electric field is going to do work on this, and it's going to push that charge, okay, towards the negative charges. This is exactly the same thing as you would have when you had a mass in a gravitational field. If you leave that mass up in the air, well, then the gravity is going to pull it down. If you leave a positive charge, okay, in an electric field, it's going to get pushed away. So now the question arises, okay, well, this has a certain amount of electric potential energy. And this is the electric potential energy, and this right here was the gravitational potential energy. So they're kind of analogous in some particular way, except one has to do with charges and one has to do with a mass. So now if you have this electric potential energy, so now we can ask the question, well, what is going to happen to this charge? And if this charge gets moved, so if I duplicate it, or I brought it, if I brought this back down here, is it going to gain potential energy or is it going to lose potential energy? Well, it's the same thing as the mass. As the mass comes closer and closer to a reference point, okay, so let's say to the Earth, well, it's losing potential energy. The actual charge, the positive charge, because it's very close to the positives, as you can see there. So if that electric field is pointing downwards, well, if this is going to be moving down, it's going to be losing electric potential energy. And now, so instead of writing, EGP, I mean, what acronym you put there does not matter. So I, for instance, put in here that I'm going to use, okay, so this is the energy, this is the difference, the potential difference. So this is the electric potential difference. All right, so I put EP, okay, GP for gravitational potential difference. And now the question arises, why in the world is it this, right? And then how do we decipher what the sign will be in here? Okay, so if you now still stick with this positive charge that we have, so that particular positive charge, okay, so let's say that it was somewhere over here, what we're saying is that it will be losing potential energy, okay, if it was going downwards. Now, and if it was down in here and you would have been trying to push it upwards, that means you were going against the electric potential, kind of the electric field. So therefore you would have to do work. So if you would be lifting this up, this would be gaining energy. So this down here, it's going to be losing energy, okay? And this right here, it's going to be gaining energy. That's what's going to happen. Now, how much, okay, potential difference energy will it gain or lose? Well, this comes back to this equation once again, okay? Well, how much work is it going to be done? Now, within here, so again, you can see, especially in the beginning stages as you're learning this, the angle is basically going to be 0, or in fact, or 180 if you're going in the opposite direction. So the actual number there is either 1 or -1 for cos of 0 or cos of 180 degrees, depending on which direction you're moving. And then the question is, okay, well, then what's the force, and then what is the displacement? Well, the displacement that we have is the actual displacement from the initial, okay, to the final. So if this was your initial position that you have, and then this was right here your final position that you have, then surely we can define what the position, okay, or what the actual difference is, which would have been just df minus di, and then we can find out exactly what that is. Now, just like anything else when you're doing work, because it is defined with respect to the displacement, that means the path doesn't matter, right? It's not the distance that you travel. So it's not like you take this and you move it around, right? It is actually from the initial to the final. So the displacement is going to be this distance. And if your electric field, okay, is pointing in the direction that you have there, well, what's the electric field defined as? The electric field is defined as, we have it, okay, so this is from right here. And if we know that electric field, we know exactly what the force applied is. What's the electric force on that charge? And that is just Q, okay, which is the charge. In this case, it's a positively charged item. And then what the electric field will be. And you can see that this is exactly what shows up over here, because this is nothing else but just simply the actual force. So this is the force multiplied by the displacement, which is the work which is done, right, okay, on the object, or which is taken away from the object. So we know that work is the force times the displacement in terms of the items. So therefore, as you are working through this is going to be, okay, so if you're thinking about work, I'm going to just write work within here. It's going to be the force. Well, the force is just Q times the electric field. I'm going to drop the vector, okay, so within here. And then it's going to be multiplied by the actual displacement. And again, let's just assume that it is, okay, with respect, okay, to just scalar values, so magnitudes, instead of worrying about the vectors themselves. Although you can certainly throw in the vectors, okay, if they have different angles. But in this case, you know, we're going in exactly the same direction. So that is the work. And now that work would have been the potential energy difference. So what is the difference in the potential? In this case, it's electric potential. So that electric potential, so that particular difference that we have, is equal to the amount of work, okay, which is done. And now the question arises, all right, is it positive or is it negative? Well, we define it with respect to a positive charge. And if it's a positive charge within here, so then what would happen is if you do take this positive charge, let's imagine it's a proton. Then if you take this proton and you move it with the direction, okay, of the electric field, so if it moves all the way down here, then now the question arises, did it gain or did it lose the actual energy, its potential energy? Well, it was losing potential energy. And therefore, since it was losing this potential energy, okay, as it moved downwards, then we define that the difference is negative. This is purely by convention. But you yourself should remember, okay, is it losing, therefore it's negative, or is it gaining, and therefore it will be positive? So if you're going in one direction, so if you're going in this direction and it's a positive charge, then it's going to be losing potential energy. If it's a positive charge and you're going in this direction, then it's going to be gaining, and therefore this would have been positive. Now, in the definition itself, so if you would substitute all of this in here, so it would have been negative Q, so this is the positive charge, this is the magnitude of the electric field, which is in the direction of the motion, and then this is your displacement. So this is really the definition that you have, and the negative sign is just because it's a positive one and it's moving in the direction of the electric field. Okay, if it was going in reverse, okay, then all of a sudden, okay, that reverse, well, the displacement you can think about is now in the opposite direction, so therefore the two negatives would have canceled out and it would have made it positive. I like to always think about, is it losing potential energy or is it gaining potential energy? And it is defined with respect to a positive charge. But now you might ask, well, what if it's a negative charge? Well, in that case, if it was negative charge, so if you would take this instead, so if I take these two, I'm going to duplicate it. Okay, I'll put them over here, and I'm going to now remove. So what if it was just now a negative charge? Well, so now think about what happens, right? So when you have a negative charge is attracted to the positive side. But our electric field, by convention, is always defined from positive to negative. So it goes downwards in this case. So therefore, the signs would have been flipping now for us. Because if we now take this, which is now, let's say, maybe an electron, okay, or some kind of a negatively charged particle, and we start moving it in this direction, okay, so as we're getting closer and closer to the negative side. So we're going in the direction of the electric field, but the electric field has been defined with respect to positive. So really, is this now gaining potential energy or is it losing? So think about that. So this object, which was the positively, this was losing potential energy. And therefore, if this one is negative, this one is gaining potential energy if it goes in this direction. And if it goes in the opposite direction, so if it's going in this direction, now it's losing potential energy because it gets closer and closer towards the positive side. Right? So that's exactly what it wants to do. It's the same thing as the mass. Okay, as the mass goes in and gets closer and closer towards the Earth, therefore the height reduces, therefore it's losing its potential energy. The only tricky part is that in electric charges, they can be positive and negative. So unlike a mass, where there's only one thing that can happen, right? It can just get pulled down in the gravitational field. There isn't a positively charged mass and a negatively charged. I mean, of course there can be, but then they're charges. But mass is positive, right? So because it's the amount of matter that we have. In charges, we can have a positive and negative. So the only thing that you should think about is when you're doing your thought process and calculation, always think in which directions, okay, are you going along. So just to summarize this, we know that the actual formula is this: the charge times the magnitude of the electric field times the magnitude of the displacement. And always think about, are you gaining or are you losing potential energy? And that is the difference that you have. So did you gain some or did you lose some? That's what electric potential energy is. So here is if you have an electric field, okay, and it's in this direction, and now you take a positively charged item. So let's say it's this item. Now a little bit of a test for you. So if I would move this, okay, from here to here, now the question arises, did it gain potential energy or did it lose potential energy? Therefore, is that difference positive or negative? So when it is a positively charged, if it's moving in the direction of the electric field, then it's going to be losing potential energy. If it is moving in the opposite direction, so if it's going against the electric field, then it's going to be gaining, so it's going to be positive. So that's how you can think about that. And if it, on the other side, if it is now a negatively charged, it does the opposite. So if it is moving in the direction, so as it moves in the direction of the electric field, remember positive one is losing, so a negative one is going to be gaining. Okay, and if it's going in the opposite direction, then it's going to be losing. So that's for the negative. So I always try to remember just the positive, and then what happens with the positive, and obviously the negative will be flipped around. All right, so it's always worth seeing an example. I'll put up a link to an example once I do one, okay, so that you can do your calculations within it. So now I hope that you have some understanding of what this electric potential energy difference is, because you do need to understand it if you want to slowly get into and really understand what voltage is. All right, thanks for watching. We'll see you in a future video. Bye, everybody.